Okay, so section 10.2, we actually get to do some hypothesis testing. So this is going to mirror what 8.1 and 9.1 did. So we're going to do hypothesis testing for population means when we know what sigma, the population standard deviation, is. So this this second section is going to be a little bit longer than some of the other ones in terms of the terminology. So we have three objectives to get through in this section. The first is to discuss our what we call rejection regions. And this will be the most in-depth we talk about rejection regions in this chapter because they are basically the same for each hypothesis test, which is nice because it means we don't need to relearn things or learn new stuff. We just learn it once and then it's the same with different statistics. And then we're going to talk about the testing of an alternative hypothesis. So this is the kind of quirky thing about hypothesis testing is we refer to it as testing the alternative because we're trying to see if that alternative is a good alternative, even though our conclusions are always based on the null hypothesis. So just a little bit of a quirky thing. And then we'll talk a little bit about p-values, probability values, or areas under the curve. So remember the test statistic is our sample statistic. So for this section, it's our standard score, but for samples. So this will be x bar minus mu over sigma over square root of n. Right? Just that sample standard score that we looked at in the previous couple chapters. So our rejection regions. These regions determine the result of the hypothesis test. They're based on two things. Number one, the type of test. So means, variance, etc. And the second thing is the level of significance, or alpha. Now, you probably are thinking, well, he just said that the rejection regions are similar all the way through. They are similar. They're almost the same thing. What I mean by type of test is there are certain types of tests that appear more frequently. So for mean hypothesis testing, you're going to see a less than versus a greater than or equal to, or a greater than versus a less than or equal to test in your hypotheses more often than you see the equal or unequal. Excuse me. In something like proportion, you usually see when you're testing population proportions, you see equal to unequal. Right? We think that it's 92%. We want to see if that's different. So there are three types of hypothesis tests that we look at, and this is really what we mean by the type of test. So the mean, what statistic you're testing does play some role in terms of how frequently you see it, but you can see all three types of this test when you are testing any of these things: means, variance, proportion, paired differences. So they're all based on the alternative. So the test, again, is we're testing the alternative hypothesis, but our conclusions are all in reference to the null hypothesis. So if H sub A is less than B is our alternative. So this is I don't know how to write this. Let's just say, let's put a generic X in here, is less than B. Then what we have is a left tail test. Which means we're looking at the left side of our distribution, whether that be the normal, the t, or the chi-squared. Number two, if H sub A is something like X is greater than B, then we have a right tail test. So we're looking at the right side of our distribution. And then the last one is if our alternative is something like X is not B. Now I'm using X as just a generic X, not anything that it's going to be, because what we'll really be looking at is Z's, T's, and like P's. And so this, when it's not equal, is two-tailed. So now that we know the types of tests, we can actually go into more detail about the rejection region. So let's look at the rejection regions for the left tail test. Now, I've got this weird box that when I made this bigger for you all, it just wreaked havoc on my formatting, but that's okay. So if we draw ourselves a little distribution, we'll use the normal as our example here, but you can draw the t-distribution or a chi-square. Well, you don't know what a chi-square looks like yet. But we have a left tail test. So we're looking at the left side. We would look at this value here. And this would be z sub alpha over 2. And so in a left tail test, we are comparing our test statistic z, and we want to know, is it less than or equal to this? I should say this is negative. Z sub is negative z less than or equal to negative z sub alpha over 2. Now, actually, we don't do negative, because if it's negative, it'll be negative. If it's positive, it'll be positive. And if this is true, then we reject our null hypothesis. Because what this means is that the standard score, this z sub alpha over 2, this is, remember, based on our confidence level. This is based on alpha. This is saying that the majority, the null, the default, should be to the right. Because we know on a normal distribution or even on a t-distribution, the tails hold small amounts of data. So if we land out here, if our z is out here, then we reject the null because we are further away from where we think we should be. And if we're anywhere to the right, we fail to reject the null. Because then we did land on the side that we expect it to. So that's for a left tail test. This is how we determine the rejection region. So you're going to be looking at this compared to your critical z-score. And since it's left tail, you're looking at the negative critical z. So let's talk about the right tail and the two-tailed. So same idea here. Give ourselves a little distribution picture. Again, we'll use the normal. So the right tail is looking at some value over here. This would be z sub alpha over 2. So since we're looking for the right tail, if we're out here to the right of z sub alpha over 2, we would not expect most things to be here. So if we ended up here with our test statistic z, we would reject the null hypothesis. If we landed anywhere in here, we would fail to reject the null. And so if basically what we're saying, if z is greater than or equal to z sub alpha over 2, we reject the null hypothesis. Because we're outside the range that we would expect to be. So, two-tailed tests. Exactly what you'd expect. They look at both tails. So we have z sub alpha over 2, and we have z sub alpha, negative z sub alpha over 2. So for a two-tailed test, again, we expect things to be in between the critical z-score. So if we hit from here to here, this is where we think it should be. This is the default, so we would fail to reject the null here. But if we landed out here or out here, we would reject the null. And so what we're really saying here is if we have the absolute value of our test statistic z is greater than or equal to z sub alpha over 2, then we reject our null hypothesis. And in reality, since it's absolute value, that means that if we have something less than or equal to z sub alpha over 2, or something greater than or equal to positive z sub alpha over 2. Because if we pop up here, we'll be greater than this. If we pop up down here, we'll be less than this. So you check both things. So let's take a look at actually running two hypothesis tests in this section. Yeah, I've got two. We got a couple other stuff on the back sides. Actually, I just realized this is a one-tailed test, so it's not alpha over 2 for the one-tailed test. It's just z sub alpha is our critical z. So if we go back here as well, this should be just z sub alpha. Okay, so just to reiterate, for the left tail and right tail test, you're comparing it to z sub alphas, not z sub alpha over 2, because z sub alpha over 2 is for two tails, right? Because we need both things. So just z sub alpha on those. Okay, so let's run this test. The education department is trying to boost reading levels. The mean reading level in 5th grade is 800L. Don't worry about that. That's just how they give the levels. The new program is supposed to raise scores by 50 or more. If the pilot study ends with an average level of 856L and sigma was 98L, using a significance level of 0.05, should the new program be adopted? Assume the study had 1,000 participants. So here's where I like to begin with these. We're going to first just identify all the information that they give us. So they tell us, let's start with what we know. The average of the study was 856L, so that's X bar. The standard deviation, sigma, they're telling us is 98L. Our sample size is 1,000. And our significance level, alpha, is 0.05. Well, that tells us our C level, confidence level, is 0.95, just in case we need that. Now that I've got all this, I'm going to go into identifying my hypotheses. So what do they believe is true, and what are they testing, or what is supposed to be tested? So this comes down to, just like some of those problems in the last section, the mean reading level is 800L. That's what it currently is, 800L. That would be the null. But what they're testing this new program, it's supposed to raise scores by 50 or more. So the alternative hypothesis that they are testing is that mu will be greater than 850. And so to fail this, you would actually be less than or equal to 850. That's the hypotheses that we're testing here. So now that we've done that, we are doing means. So that means our test statistic, our distribution is the z, is the normal distribution. So our z-score, just a little reminder here, x bar minus mu over sigma over square root n. So this is 856 minus 850 over 98 over square root of 1,000. And this comes out to be about 1.94. So now we need our z sub alpha to run our test, to look at our rejection regions. So z sub alpha is z with the score for 0.05. So this is just inverse norm in the calculator of 0.05. And we get this to be 1.645. Excuse me. So what we are looking at here is, based on our hypotheses, this is a right-tailed test. So we look at our z-score, our test z-score, 1.94. This is greater than 1.645. So in our rejection region, we are over here. So we're going to reject the null hypothesis. We're not saying that the alternative is true. Remember, it could be wrong, and also was only 1,000 people. We say we reject the null hypothesis, and what we do then is say, based on the data, so we say at this significance level, the data suggests that the claim is true with 95% certainty. And the phrasing here is very important. One, you have to say that at this significance level. Two, we have to say that the data is suggesting the claim is true, not that the data is saying the claim is true. All right? This phrase, this sentence does not say that the claim is true, this study will raise scores by more than 50. It's not saying that. It's saying at this level, we can be 95% certain that our data is suggesting that the claim is true. So, in other words, we're saying this study has had the results that they claimed would happen with these participants. We are not saying that this is true for the population. That's the big thing about hypothesis testing, is it is completely drenched in caveats and vagueness on purpose because we could be wrong. We could be, this 5% chance we're wrong here. Now, we don't always want to look at the z-values for the rejection regions, so we can use the p-values, the probabilities. So this is a value that represents the probability of obtaining a sample statistic as extreme as the one observed in the data. So remember, the data is a sample, so we can use this 1,000, this education one as our springboard here. This is a sample of 1,000 people. It got an average of 856. That is extreme compared to the default or the historical mean. So our p-value of our data result tells us the probability of obtaining a sample statistic in another sample of at least that size of different random samples that we observed when we assume the null hypothesis is true. And so to do this, to use the p-value, first you find z sub alpha, or for the two-tailed test, z sub alpha over 2. And then you find the probability that z equals z sub alpha. So here we have a little example just to get us used to calculating p-values again. So we have two hypotheses. Our null is that mu is greater than or equal to 0.15, and the alternative is that it's less than 0.15. And we have a test statistic of z equals negative 1.34. And so to find this, we would just do p of z equals negative 1.34, which we know is the same as p of z is less than or equal to negative 1.34. And so remember, that's the normal CDF in the calculator. And this is a left tail test. So our lower bound would be 1e99 comma negative 1.34, because that's our upper bound. So we want to see what's the probability we hit the left tail. And this gives us approximately 0.0901. So the probability that we get something in another sample as extreme as this value is 0.9%. Oh, I did forget something. We find p z equals z alpha, and p of z, all right, which is what we did here. Now we're going to combine these two in the next section, in the next box here. So this is just to remind you how to find your p-value. So when you interpret a p-value, if the p-value is less than or equal to alpha, which is what p of z alpha is, then you reject the null hypothesis. Now the nice thing is this is true, period, no matter what type of test you're doing. Because what you do is compare this to alpha, so we don't have an alpha here to do it, but we'll see it in the next example. Your alpha is your significance level. So whether it's a left tail, right tail, or two-tailed, you're always going to have one single significance level. If your p-value of your z-score for your sample is less than or equal to alpha, you reject your null hypothesis, because that means you're in the tails. You're outside that z sub alpha, or z sub alpha over 2. If your p-value is greater than alpha, you fail to reject it. So let's take a look at an example how we would do this. So a researcher claims that the mean age of women in California when they marry is higher than 26.5 years old. A simple random sample of 213 newlywed women found a mean of 27 years. Assuming population standard deviation is 2.3 years and a level of confidence of 95%, determine if there is evidence to support the claim. Oh, I'm reading the next one. I'm sorry. I apologize. We're doing basic one first. For a certain hypothesis test, a p-value is found to be 0.0146. If the significance level is 0.05, what is the conclusion? So our p-value was 0.0146 compared to alpha, 0.05. Well, this is less than, so we would reject the null hypothesis, because that means that we were further to the left or right, or in either case, in the two-tail case, on one of the tails, than our critical z-score. In part B, if our confidence level is 99%, that means alpha is 0.01. And so comparing 0.0146 to 0.01, this is actually greater, because this is 0.0100. So even though this is only 46 hundred thousandths, it's still bigger. And so here we would fail to reject the null, because this means that we are to the right in a left tail, or to the left in a right tail of that rejection region. We're towards the center more. So that's just how we interpret it. So now we can do the hypothesis test that I just read out to you. So again, researcher claims age of newlywed women is 26.5 years old. Simple random sample of 213 found it was 27 years. Standard deviation of the population we're going to assume is 2.3 years. Level of confidence is 95%. And we're going to determine if there's evidence to support the claim. So let's start with trying to identify our null and alternative hypotheses. So they think it's higher than 26.5. So they think that the average age is greater than 26.5, which means that the null is that the age is equal to or greater than, or I'm sorry, not equal to or greater than, less than or equal to 26.5. Because in either of these cases, their claim would be wrong. So now we can identify our stuff. X bar, they found to be 27. N was 213. Sigma, we are assuming, is 2.3. And C equals 0.95, which tells us that alpha is 0.05. So based on our alternative here, this is a right tail test. Because we're greater than 26.5, we're pointed to the right. So now we can calculate our z-score. 27 minus 26.5 over 2.3 over the square root of 213. And this comes out to be about 3.17. So now we look at the probability that z is greater than or equal to 3.17, our p-value. Remember, this is normal CDF. Your lower bound is now 3.17. Your upper bound is now 1E99. And I get about 0.00076, so I'm going to round this to 4 decimal 0.008. So now we have our p-value. Compare that to alpha. which is 0.05, alpha is way bigger. Way bigger. Magnitudes bigger. So that means we are to the left of our critical score. So since this is a right-tailed test, if you think about the distribution, here's z sub alpha, we are over here, which means we fail to reject. Oh, I'm sorry. We did p-values. I'm thinking the next section where we compare. We reject the null hypothesis. Because what we actually are, since our p-value is so small, if this is z sub alpha, that means that this whole area here is alpha. Well, if this is alpha, to be less than alpha for our p-value, we have to be something like here. This is where our z-score lives, somewhere in there, to the right, even further. Because remember, alpha is area under the distribution curve. So this is our conclusion we have to interpret. So we can say we are 95% certain the evidence suggests / supports that the claim of mean age of newlywed women is greater than 26.5 years. And holy moly, I just saw the time. This was a long, long video. I apologize.